Hi, everyone. What motivates miners regarding Bitcoin? What's their incentive? What's the point? And so I wanted to just quickly say that the point is that they earn a reward for mining. And uh, the reward is different over time. It's dependent upon price, which you can see here. Since 2015, there has been uh, extreme volatility in general cryptocurrency prices. This is Bitcoin here, and you can see that we're in another large sell-off at the moment. But so the rewards are based on two things. It's the price of what the coins are, and also what current halving cycle we are in. And every 4 years, the amount of Bitcoins that are released for a mined block is decreased by half. So it started at 50 back in 2009. It went to 25 and then 12 and a half. And we're currently in the third halving cycle, which means every time a block is mined, 6.25 new Bitcoin are created. And that goes to the miner. So that's an incentive and a motivation for a miner who cares nothing other than their own profitability and selfishness. That's their motivation. The current price of Bitcoin is $21,403. If you get, let's see, if you get 6.25 every 10 minutes, which is when the average block is mined, you will get you'll make about $133,000 in 10 minutes. So if your computers can outperform the others, you'll receive that reward. So if you do that 6 times in an hour, that's 800,000 US dollars, the equivalent of what a Bitcoin is trading at on the market. And in 24 hours, that's almost $20 million. And across an entire year, at current prices with the current halving cycle, that's a little over $7 billion. So that's a motivation. And the next part of that question was, so the network holds a lottery. And here's a description from another site. Every computer on the network races to be the first to guess a 64-digit hexadecimal number known as a hash. That's right. And the first to guess means there is no shortcut to determining what this hash is. And so that's what the limitation is, and some of the initial conditions of the puzzle mining process. Mining is, of course, a mathematical concept. It is not physical concept. And you can use the word lottery here because if you are successful in guessing that correct hash, then you win the Bitcoin reward for that block. Let's look at an example. Here is a very basic block of data that would represent something we'd see in Bitcoin. It has an ID here, which is a hash. And then it has this header, which is made up of three things. The transaction summary, which this block has transactions that have values of 12, 2, 14, 9, 0, 17, and so on. This is a toy example. But these transactions, if we hash them into a single hash, we'll get this transaction summary. And so we know that in order to produce this transaction hash, it has to include these transactions. Okay, so now we know that we have an identifier for all of the transactions in this one hash. We also want the previous block's hash, which includes all of its data from the previous block And we know if anything were to change there, it would not match this hash ID. We add a timestamp, and then we take this header, we hash it. So we're going to hash the timestamp, the previous block ID, and the transaction summary, and we're going to produce this new ID. This will go into the new block and represent that block's hash. Okay, so what is given about the number that's being guessed in the mining process? If we do some Wolfram code here, and we want to get blockchain block data for the last block of Bitcoin and put it into a data set, we will get this. This is the last block on 15 minutes ago, it appears. And what it has here is this block hash. This is the ID of this entire block. And these 19 zeros that exist here is the targeted hash that we're looking for. So miners are competing to produce a hash that looks exactly like this with this amount of leading zeros. How would we guess what that hash is? Well, if we take a hash function and we say, I'm putting in a string, and I would just want to say, what will produce the hash we see below? And I'm going to use the SHA-256 hash algorithm, and I want to output as a hex string. And this is the hash produced by this input. If I was to change anything about this input, like remove a question mark, it'll be a completely different hash. And what the miners are doing is some function to guess what hash will produce the output that has this many zeros at the beginning. That seems simple. But what we want to do is iterate on a single number called a nonce, and we set it equal to, say, 1 in the beginning. And then we run that. And that did not produce the amount of zeros in the beginning of the hash that we wanted. So we iterate again. We say 2. Well, of course, we can't do this by hand. So we need something that's going to guess a little more efficiently. And so we're going to create a table of hashes, and we're going to try 10 of them at a time. We can see these 10 hashes, one of them produces a 0 at the beginning, but we need a bunch more zeros. And it turns out that it takes, with the current amount of hash power on the network, about 10 minutes to find the hash that fits this target. So if I add 100 hashes and I go through here and I search, here's one that starts with 2 zeros. But that's far from 19, the target that we currently need. 19 is just arbitrary. That's what it's currently set at. So let's just try 1,000. And so we have our computers autonomously guessing because we don't have a shortcut in order to produce the hash for the right target. And we just search until we find one. And once we find one, then we publish that block and we distribute that information to all of the other nodes running in the network. And we say, using this previous hash ID and using the transaction summary hash and the timestamp and this specific nonce, we can produce the right hash output. And that's essentially what the puzzle is. That's the puzzle that each miner is trying to solve. the question is, why can't I just add zeros to the beginning that will produce the hash that I want? And what you need to include to demonstrate are these specific inputs: a transaction summary hash, a previous block hash, and a timestamp, along with a nonce. So it's a number used once. That's what a nonce stands for. That nonce essentially says this is the number that had to be used in in um, in accordance with the other header information to produce the hash with the right amount of zeros. It is a combination of many things that produce that one, but that nonce is, it cannot be used again. It's that number used once. It's the thing that the miners iterate through in order to find the targeted number. Why is the amount of zeros so critical? If in our exploration, I think it was with just 10 guesses, we were able to find a hash that began with 1 0. And in our search of 100 hashes, we were able to find a hash that began with 2 zeros. Yes, here's one. Essentially, we don't know what can produce a hash beginning with any number of zeros. And so what's included is what's focused on is the difficulty adjustment number. At the very beginning of Bitcoin, at its inception, there may have only been one miner mining in this computer algorithm. That might have been Satoshi Nakamoto. As the idea caught on, maybe a few other miners joined the party and began mining. If you flood the system with too much computational power, you won't produce a block on a average 10-minute time scale. And that 10 minutes, again, it was important because that's the amount of time to um, that's the amount of time that we want to give a buffer for when distributing that information to the whole network. We can generally do it in a shorter time frame than 10 minutes. So we're distributing that information. We want it to proliferate across the entire network, and we give it 10 minutes in order to do that. Okay, so we need to align the incentives of the participants within Bitcoin, within a blockchain network, right? If it required nothing but an IP address to participate in the system and receive the reward, then whichever entity could produce the most IP addresses would essentially have the dominant share of the lottery, the chance to win. So what's required here in the mining process is this proof that you are doing some amount of computational effort, expending electricity, that says I'm willing to spend this electricity, which costs money, which is an effort, in order to demonstrate that I'm aligned with the system. And if I am aligned with the system, then I'm able to receive a reward. Is it true that there's no inflation in Bitcoins? If so, why is that? No inflation, meaning what's built in is this 21 million Bitcoin hard cap. There won't be more than that. And so you can say that the inflation is every time one new block is produced, 6.25 is popping out currently, and that's what the inflation is. But there's not going to be any more added to the system, and it would take it would it would it's something that's um, it's not theoretically impossible to change that because it would take an enormous amount of consensus to fork the system, to implement new code in order to um, change that 21 million supply cap. But it's infeasible, and if it did, it would be on a different system. It wouldn't be Bitcoin. Okay, I'm going to move along. We're going to continue looking at kind of a toy blockchain example here. So if we want to build our own blockchain and we want to establish the Genesis block. In a Genesis block, we typically have to hard code it. That's what we're doing here for this toy example. So that's what we're going to do. We're calling it X blockchain. We need a header with a certain amount of information in it. And let's just visualize that here. We have header with transaction, single transaction in it. Now we want to generate the ID of this block. Okay, so we take the timestamp, the previous block ID, and the transaction summary, and we make hash out of it. That's what we're going to do here, and then we prepend that output to the Genesis block, and then we can look at it down here. So this is our Genesis block. It has an ID, the header, transaction list. Great. What do we do with that? Now we want to verify that a block matches its previous block ID. And so out of X blockchain, we're going to take block number 16 and number 17 here. And let's look at 16 is the previous block. So we take its ID ending in E9F86. And we see in this block 17 header that the previous block ID is identical, E9F86, to the previous block. This just tells us that we have a link between one block to the next. So if we say same queue, the header of the block ID with the previous block ID will get true. So we can tell that we have a link there. If we produce a bunch of blocks, this is what they look like, and you'll be able to see that the previous block ID will match the block before it, and so on and so on and so on. And for Bitcoin, we're at about over 700,000 blocks. You can run that all the way back to the Genesis block. Now, what happens if we modify a block? Let's say I want to spend an additional transaction in a block in the past. What happens? Well, what I'm going to do here is take a transaction list, and I'm going to add to that transaction list one transaction. I'm going to create a block with that additional transaction. We're going to take the previously established data set of block 16 and compare it now with the new transaction included in it, 21, and say, does block 16 match block 17? And the outcome is false. What that gives us is some assurances throughout history. It says this chain is immutable. It says with the link of hash functions, we can say nothing's been changed here. And if it was, then we won't accept that block to be validated. And in that way, we can say with cryptographic security that this is an immutable ledger. And that's an important thing to have.